All right, well, hello AP Physics students, and welcome to this video lecture. It's going to introduce you to work and energy. First things first, I guess, what is work? Work, we say that work is done on an object when a force causes a displacement. Okay, so if a force causes a displacement of an object, that means that work has been done. So that's kind of our verbal definition for work. We have a mathematical definition for work like we do with most things in physics. And our mathematical definition is that work is equal to force times a displacement, and then that's times the cosine of theta. Okay, so again, this is force, this is displacement, and now this cosine of theta is kind of weird, but what this angle is, it is the angle between the force and the displacement. Okay, now that'll be cleared up in a couple examples that I do in a little bit here. One other thing with work, our units for work are these things called joules. Okay, so work units, I don't know why I put equals. So work units are joules, and a joule is a Newton meter. Okay, a Newton meter. And that should make sense because in our work equation, force, our units for force are newtons, and our units for displacement are meters. Okay, so we shorten it up and we say joules. Okay, so our example here, to kind of get us understanding how we use this equation and what this angle theta actually means. Let's say that I have a box and there's an applied force on that box of 10 newtons. And that box, because of that force, gets displaced 5 meters. Well, let's figure out the work that's been done there. So work is equal to our 10 Newton force times that 5 meter displacement. Now, that's going to be times the cosine. Now, what's our angle here? Well, our force is going this way, our displacement's also this way, so the angle there is just 0. Okay, they're in the same direction. So cosine of 0 is just 1, so the work done in this scenario then is 50 Newton meters, which we can then simplify and say 50 joules. Okay, I want to do one more example here. Let's see if I can erase this quickly here. Oh, no, not that. There we go. So I'm going to erase this example here. Now, let's say that I have a tray of food. Okay, let's say I'm a waiter and I have a tray of food here. Put a Granny Smith apple there. Wow, that's a really bad apple. Okay. And let's say that there's some force being applied to that tray of 10 newtons, but that tray of food is being displaced around the room by the waiter 5 meters again. Okay, so let's try and figure out what the work done is. So we have our 10 Newton force, we have our displacement of 5 meters, and now our cosine, well, the angle here, we have our force going this way, but we have our displacement this way. So that's an angle of 90 degrees. Okay, because this force and this displacement are perpendicular to one another, so that angle is 90 degrees. Well, the cosine of 90 is 0. So our work done in this scenario then is 0 joules. So what does this mean for us? Well, what this means, and we can go right back to our definition, okay? That force has to cause a displacement. Yes, in this scenario, we have a force being applied, but that force is not causing this displacement. So again, we cannot say that work is being done by this force. There may be another force here that did cause this displacement, and we know that that's a thing, but based on just this force, there is no work being done by this force because it's not causing this displacement. All right, now moving on from work and starting to talk about energy here. Energy is a weird thing. It's kind of an abstract thing to think about, and it really has no meaning until we attach some math to it. So what is energy? We say that energy is the ability for an object to do work. Do work? Okay, so energy is the ability for an object to do work. And energy is a scalar quantity, just getting that out there. Energy is a scalar quantity. Now, there's some different types of energy that we can talk about, and that's how I'm going to introduce energy to you in this video lecture. Now, we have this big, broad category of energy, which is called mechanical energy. And this is the type of energy that we're going to be looking at most often in this class. So mechanical energy is just the energy possessed by an object due to its motion or its position. Now, we can break mechanical energy down into a couple different types of energy. And the first that we can talk about is potential energy. Now, this is the energy that an object has based on its position. And the key here is that it's stored energy. So one of our major types of potential energy is this thing called gravitational potential energy. Okay, and our equation for gravitational potential energy is mass times the acceleration due to gravity times height. So gravitational potential energy is the energy, the stored energy an object has based on its position from some reference point. Okay, so this is gravitational potential energy. Gravitational potential energy. Okay, so just a quick example here. Let's say that I have a ball sitting on top of a cliff, and it's at some height. Okay, it's at some height above this reference point on the ground. Okay, so because this ball is at some height above our reference point here, it has some amount of gravitational potential energy. It has the ability to do work, but it's just not quite doing it yet. Okay. The next type of potential energy that we will discuss in this class is elastic potential energy. And this is the energy that a spring or some elastic type object, maybe a rubber band, has based on its configuration, or maybe a better word to say would be deformation, because we know that elastic objects like springs can be compressed or they can be stretched out. So our equation for elastic potential energy is 1/2 kx squared. And again, this is elastic potential energy. Now, this equation should look a little bit familiar to you when we talk very briefly about Hooke's law and forces on springs. So this K here is just our spring constant, and then our X is our displacement from some equilibrium position. So, if we have a spring here, and that's its relaxed position, its normal position, and we stretch it out some amount, okay, that's X, okay? And we're going to talk much more about these types, but I just want to introduce these to you. Now, moving on from potential energy, we also have this thing called kinetic energy. And this is the energy an object has based on its motion. Okay, so this is essentially motion energy. And we have an equation for kinetic energy as well. We say that Ke is equal to 1/2 m v squared, okay? M, again, being the mass of that object, and v being the velocity that that object has. Now, a really important thing to note with all of these different types of energy is that the units for energy are joules. Units for energy are joules. Now, it's no coincidence that work and energy have the same units. And tomorrow in class, we're going to be discovering how work and energy are actually connected. So I hope that this tutorial kind of shed some light on these two things called work and energy. Again, this is just a very brief overview. We're going to be getting much deeper into these ideas in the coming weeks. So take care, AP Physics students.